What do we do with matrices? Mostly, we multiply them by vectors. There are two ways to multiply a vector in a matrix. One is called matrix vector multiplication, and the other is called vector matrix multiplication. For each of these, I'm going to give two equivalent definitions. And which definition is most appropriate depends on the situation. We start with the linear combinations definition of matrix vector multiply. So, given an R by C matrix M, if V is a C vector, then the product M times V is the linear combination of the columns of M where the coefficients are given by the entries in V. So, for example, given this matrix and this vector, we take the product by multiplying the first entry of the vector by the corresponding column, the second entry of the vector by the second column, and the third entry by the third column. So we get this. On the other hand, if V is not a C vector, then the product M times V is not even allowed. So, for example, this matrix vector product is an error because the number of entries in the vector isn't the same as the number of columns in the matrix. Here's another example. The product of this matrix by this vector is obtained by taking this entry of the vector and multiplying it by this column of the matrix. This entry multiplied by this column, and this entry multiplied by this column. And here's the result. Recall the lights out puzzle. We said that a solution to a given configuration for lights out is a linear combination of the button vectors. And we can write a linear combination as a matrix vector product. For example, this linear combination, which expresses this configuration in terms of button vectors, can be written as the matrix vector product, where the columns of the matrix are the button vectors. And the vector specifies the coefficients in the linear combination. Solving an instance of lights out, therefore, can be expressed as solving a matrix vector equation. That is, given the desired configuration and given the matrix, find the entries of the vector such that the matrix times the vector equals that desired configuration. This is a fundamental computational problem, solving a matrix vector equation. The input is a matrix and a vector, and the goal is to find a vector x such that A times x equals B. Here's a way to solve the special case where the matrix is 2 by 2. To solve an equation of this form, we require that AD is not equal to BC. And if that's the case, we solve by setting x equal to dp minus cq over AD minus BC, and y equals AQ minus BP over AD minus BC. So, for example, to solve this matrix vector equation, we would set x and y according to the formulas. Later, we'll study algorithms for the more general case. Vector matrix multiplication is different from matrix vector multiplication. Let's start with the definition of matrix vector multiplication. Remember, it's the linear combination of the columns of the matrix with coefficients given by the entries of the vector. Here's the definition of vector matrix multiplication. To multiply a vector W times M, you take the linear combinations of the rows of the matrix M with coefficients given by the entries of the vector. So, for example, multiplying this vector by this matrix, we take the linear combination of the two rows with coefficients equal to the entries in the vector. You remember our Junko example from a while back. Junko makes a bunch of products, and for each one uses a certain amount of each of these resources per item. We can write this data as a matrix. Now, the total resources used equals this vector times m, where the entries of the vectors tell us how many of each item are being manufactured. Recall that in industrial espionage, we might want to calculate how many of each item Junko is produced, assuming that we know the total resources used, and of course, we know the matrix M. To find the number of items produced, we would solve a vector matrix equation, B equals x times m, where B is the vector of total resources used. So again, solving a matrix vector equation is a fundamental computational problem. And of course, if we had an algorithm for this problem, we could use it to also solve a vector matrix equation just by using the transpose.